There's many other types of trees that have been studied. It's a very huge topic. And I've really only talked about a few binary trees and binary search trees. I talked at the beginning about general trees and how they relate to binary search trees, and some of the results translate over, and many of the techniques do as well. But we're going to save a lot of that for analytic combinatorics in part 2, and we'll do many other examples then. But I do want to talk about the other types of trees that can come up briefly to prepare people for the kinds of ideas that we'll be looking at. Classically in mathematics, mathematicians talk about classic structures known as the free tree. That's just a connected graph that has no cycles. If you distinguish a root node, that's called a rooted tree. And then there's ordered tree where the order of subtrees is significant. And what we've been talking about, what I defined at the beginning, is really an ordered tree because usually in computer implementations, we pick an order because we have to represent the thing in some way. And this little diagram illustrates the distinction between these types of trees. This is 5-node trees. There's only 3 different free trees of 5 nodes. Again, these trees are defined just in terms of their connections. There's no root and there's no order. So either 4 other nodes are connected to 1, or there's 1 node that 3 are connected to, and then there's another one hanging off, or they come in a line. That's the only 3 free trees of 5 nodes. If you pick a root, but you don't care about the order of the subtrees, then there's 9 different rooted trees. In the first case, there's no difference, but in this second case, you can see that the tree on the left, there's a root that's got 3 children, and then the one that's hanging off could be in any one of the 3 children. In the case of rooted trees, that's not significant, so there's only 9 of them. And then, as we saw, there's 14, a Catalan number of ordered trees where the order is significant. Now, in this diagram, each one of these gives us a counting problem. So, we'll see that people have solved this counting problem for these types of trees. And also, you can label them and treat them as labeled structures, and then have orders on the labels, and many other kinds of problems come up. And we'll examine plenty of those in analytic combinatorics. So stay tuned for part 2 of the course. In algorithmics, there's plenty of natural ideas that come up as well. What about having more than 2 children? Why not have exactly 3 children or exactly 4? And there's plenty of applications where we might want to do that. So there's the idea of the T-ary tree, where each node has exactly T children. Or maybe there's a bound on the number of children. So each node has at most T children, but not necessarily exactly. So that's a T-restricted tree. And then there's something called the 2-3 tree, which is actually the method of choice in symbol table implementations, and that also generalizes to multiple. And that's where you can have more than 1 key per node. It's kind of a strange structure, but actually it's easy to represent as a binary tree, and I'll show that in a second. And again, all of these are going to give rise to enumeration problems for any value of t, path length, and all sorts of other things that we might want to analyze. All these different variations, just so far I've talked about 12 different types of trees and more, emphasize the need, why we need general tools like analytic combinatorics that can get us the solutions to problems without necessarily going into the details. It's why we need the general theorems that we've talked about a little bit, and that we're going to talk about more later. You can already easily see how easy it is to specify structures like this. I'm not writing it down here, but you can certainly take the defining construction for binary trees and extend that to do ternary trees or 4-ary trees. And now you know that if you can do that, then you have a generating function equation. Now, a lot of these generating function equations are not as simple to solve or get asymptotics for as the Catalan, but we will learn techniques for that. But at least I think people in this course are convinced that we can get to generating functions pretty quickly for all these types of structures. But again, that's a topic for part 2 of the course. I want to finish just by talking about one unsolved problem that is related to the things that we've been talking about. So in the real world, it's not enough to rest our faith in the use of an algorithm on this assumption that the keys are going to come in random order. They might not come in random order, and we want guaranteed performance. And there's a method for getting guaranteed performance that's based on trees called balanced trees. That's a method of choice. They're the method of choice because they're extremely simple search code. In fact, you can use BSTs. You can represent balanced trees with BSTs. So much of the code is very much the same. There's only a slight extra overhead for insertion, and you can read all the details in section 3.3 of algorithms. And it guarantees, with that slight overhead, you can guarantee that no matter how the keys are inserted, the height is going to be less than 2 log n. So it's going to be less than twice the optimal, guaranteed, no matter what the insertion is. Most algorithms use 2-3 or 2-3-4 tree representations, which actually translate right to binary trees. And again, without going into the detail, this is just an example of left-leaning red-black trees, which are the ones that are described in detail in algorithms. And that's the 2-3 tree, and don't need to even explain what that is. There's the binary tree representation of that, where sometimes you have 2 keys per node, but you can represent that just by a left-leaning node with a special link on it. And so now we have binary trees with that little extra overhead that we have to maintain those links in a particular way. But otherwise, that's the method of choice for symbol tables. Now the question is, if you have even though we have the guarantee, we're still interested in knowing the performance if we assume that the keys come in randomly, because again, that's a reasonable model. It would be better to know that the guaranteed height was asymptotic to log n with a coefficient of 1. That'd be twice as fast. When you've got something that's in the inner loop of a major computation, speeding up by a factor of 2 is important. So we'd still like to know the answer to this question of what's the average cost of a balanced tree built from a random permutation. Now again, that's not a property of trees, that's a property of the permutation in the algorithm. The tree is just a container for the data. This plot that we've been using as our logo is related to that problem. There's one kind of balanced tree called an AVL tree, which again represents a binary tree. And this is the normalized plot of the probability that the root is of rank k in a random AVL tree. Again, that's random tree model, just like random Catalan tree model. You can specify what is an AVL tree. You can take each tree equally likely, you can develop generating function relationships and produce that plot. And what this plot signifies is it shows that sometimes the root is in the middle, but sometimes it's like 1/3, 2/3. There's 2 peaks. It's quite a fascinating plot to stare at. So there's that one. Remember, and that's good because remember, for random binary trees, we had the Catalan distribution where it was not balanced at all. It was more likely to be unbalanced. And for random permutations, it's just flat. So this looks good because at least it's trying to make the root at the middle. But still our challenge is to analytically characterize that. And that's an unsolved problem. There's that plot, and this is a empirical plot for LLRB trees. It seems to have some of the same characteristics, but still we're not close to understanding how to determine the path length of balanced tree built from a random permutation. The other one, random ABL tree and random 2-3 tree, has been studied with analytic combinatorics, and we'll touch briefly on that in part 2. Okay, so that's a brief summary of other types of trees. Now I'll talk about a few exercises that you might do before the next lecture. There's plenty of exercises on tree enumeration to check out how comfortable you are with using the symbolic method for enumeration problems. So this one is, so we've got a lot of forests. Maybe we're interested only in forests that have no singleton nodes. So the question is, what's the proportion of forests with n nodes that have no trees in them consisting of a single node? And this sketch shows that for 1, 2, 3, and 4, the answers 0, half, 2/5, and 3/7 respectively. So find an asymptotic formula for that. And again, that's just using, again, the beauty of the symbolic method is you can take the basic derivation and you can modify it and still the basic structure of it follows through to give you a generating function equation that you can find asymptotics for or explicit forms. And this is just practice in doing that. This is just a computation based on our observation about permutations in binary search trees. What's the chance that you get a perfectly balanced binary tree? And that's just a fun computation. And then this is the same kind of idea. We did parameters from trees before. This is parameters from BSTs built from a random permutation. The red ones are the average number of internal nodes whose children are both internal, and the blue ones are the average number of internal nodes that have one internal and one external. For random Catalan trees, we did before, we got the solution to that constant fraction. And so this is to compute that for random binary search trees. So in lecture 5 we talked about that, and now you can compare these results against what we got in lecture 5. That's the reading for the next lecture. Another thing that some people might want to do is to run some experiments to validate the mathematical results we've talked about. For example, generate some random permutations and build binary search trees and look at the average that you get and check that it's 2n natural log n. It's always worthwhile to do that. It's a little bit of programming, but many programmers, that's no problem at all. And maybe a little harder is to try to do the same thing for random binary trees. Are those internal path lengths n squared of pi n? How close are they? How big does n have to get to be an asymptotic, and so forth? It's always worthwhile to run experiments, and some people might enjoy doing that. And then again, just to check your understanding of the material, it's a good idea to try to write up solutions to some exercises like the ones that I gave. That's an introduction to trees.